In this session, we are going to learn about linear regression. We are going to look at some of the concepts, and we are going to look at some of the fully worked out example or fully worked out Python code for solving a problem, a prediction problem, more specifically using linear regression algorithm. Okay, so let's come to the definition. In statistics, linear regression is a linear approach for modeling the relationship between a scalar response variable and one or more explanatory variables. The case of one explanatory variable is called a simple linear regression. So simple linear regression is where you have one scalar response variable and one explanatory variable. In case of multiple linear regression, you have one scalar response variable and multiple explanatory variable. Okay, so simple is one scalar response and one explanatory variable. So the response is denoted as the y feature, and the one explanatory variable for simple linear regression is say it's the x feature, and scalar response is also termed as your target variable, and explanatory variable are sometimes termed as predictor variable or independent variable as well. So in case of multiple linear regression, you still have one scalar response variable because that number doesn't change. But in terms of explanatory variable or independent variable or predictor variable, you have multiple of them for multiple linear regression. Okay, now this definition also talks about that we are going to model a linear relationship between the scalar response and the explanatory variable. Okay, and we are going to see how what do we mean by that, or how do we create that linear relationship between our so-called scalar response, or say for instance the target variable and the explanatory or predictor variable. Okay, now what is scalar? Just to understand clearly, the scalar is a scalar number. So let's say for instance 1 2 3 4 or 1.2 1.3 5.6 etc etc. These are scalar numbers. Okay, so you have scalar, you have vectors, you have matrix. So scalar number is a singleton number, which is normally a continuous numeric variable like 1 2 3 4 or 1.1 1.2 1.3 etc. Okay, so these terms hopefully are clear, and this is a Wikipedia definition for linear regression. So what I was saying is that linear so this is the statistical definition or statistical background against linear regression. So in machine learning, more often than not, or not more often than not, it's almost always you have a mathematical computing background behind your machine learning models, or a statistical model at the background of your machine learning or predictive analytics model. Okay, so with that, let's have a simple explanation or example to understand the linear regression better. So linear regression is essentially the linear equation that we all have learned in our schools. Okay, and this is an example that I have worked out in an Excel sheet. Okay, a very simple example. Let's look at the data first on the right hand side of the screen. So we have a set of data where we have years, we have advertising spends of an organization and their sales volume during those years. So this is the data from a US based organization. What they are trying to do is that, given a quantum of advertising spend, they want to predict the sales for against that particular advertising spend. Okay, now that doesn't happen easily. They have to kind of find out what is the relationship between advertising spend and sales. Okay, so the data that they have got is in 2001 they have spent $45,000 US dollars on advertising, and they have got some $2.2 million dollars of sales. Okay, $47,900 in 2002, and they've got 2.32 million US dollars as sales. Okay, so you see that generally as the advertising spends are going up, the sales are also going up, but it's not a one-to-one relationship. It's there is some kind of relationship, you can say, you can see, but you don't exactly know what is the calculation that I can use to convert my advertising spend into the sales volume. Okay, there is no fixed calculation, right? So there is an approximate calculation. You can intuitively understand there is an approximate calculation to convert my advertising spend into the sales volume, but there cannot be a fixed calculation, right? Where you can use that calculation and use your advertising spend and get an accurate value of sales for that particular year. Okay, so what we have to do is, in this case, we have to use a machine learning model, and our machine learning model is going to be the linear regression algorithm, right? The linear regression algorithm is going to read this data, year-wise advertising spends and the corresponding volume of sales, right? And what is the problem that we are going to solve? The company wants to know the relationship between the advertising spend and sales, and I'm saying that it is still going to be an approximate relationship between these two variables. Our advertising spend is the explainer variable. So if you look at the definition again, the explanatory variable is our advertising spend and sales is the scalar response variable. Okay, and we are looking for a linear relationship which is going to be in the form of a linear equation that we have learned in schools, right? And that equation is going to be an approximate equation. It cannot be a perfect equation. It'll only be an approximate equation, and we do not know that equation right up front, right? And that is why we need our linear regression algorithm to help us with, right? So the linear regression, going back, the linear regression equation is going to look at these values. So every year the advertising spend and the sales volume, it is going to learn the relationship from this data, and it is going to create a model, and that model is essentially going to contain an equation in the form of y equals mx plus c. Okay, m is a constant value, c is a constant value, y is your explanatory your response variable, which is your sales dollar, and x in that case, in this case, is your explanatory variable or the predictor variable or the independent variable that we can use. Okay, so this problem that we are going to solve is that here is the data that we have till 2019. For 2020, 21 and 22, I want to find out if we spend $95,000 for advertising, what is the approximate amount of sales that we can expect. In 2021, if we spend an approximate an advertising, if we spend $102,000, what is the approximate amount of sales that we can expect? And that will come through the relationship our machine learning algorithm or linear regression algorithm is going to learn from this historical data. Okay, and it is going to create or come up with a approximate equation, approximate linear equation, and that is what we have got here. Okay, so if you look, this is simply done in Excel sheet. All right, and you can also do it. So we have plotted the advertising spends along the x-axis, and we have plotted the sales dollars in the along the y-axis, and we have plotted all the, so the blue dots here are all the data points that you have. So 45,000, so this is the first data point, and your revenue is $2.2 million, so which is around this in the scale of y-axis. Okay, so this is your first data point. This is the second data point, which corresponds to 2002 data, etc., etc. So we have plotted all the data points, and Excel sheet, in Excel sheet itself, you have there is an option for plotting the best fit line, and by enabling that, we got the best fit line. And there is also another option in Excel to find out the best fit equation and print the best fit equation on the graph itself, right? So Excel actually has got a nice little linear regression algorithm running behind it, and it has found out this equation for you. Okay, so for this simple cases, this is just a demonstration that we can do it through Excel also, but we are going to learn how to do it in machine learning, because Excel can do it in simple cases, but Excel cannot possibly help you in very, very complex cases that your organization needs. All right. Okay, so now hopefully this is clear, the concept of data points and plotting the data and getting the best fit line and the best fit equation. Okay, the problem statement should be clear, and as to what we are trying to do here, the historical concept of the historical data, the concept of the relationship between your explanatory variable, that is advertising spend, to the target variable or response variable, which is the sales dollar here, and our challenge is to create a relationship between the explanatory variable to the response variable in the form of a linear equation, exactly same as what we have learned in our schools, in the form of y equals to mx, where y is the target variable, x is the explanatory variable predictor, and m and c are constants. Going back, diagrammatically, this is what your machine learning algorithm is going to do during the learning process. So what you are going to do is that you have your historical data. This is your data. So in our case, this is my data, data of years 2001 to 2019. Okay, so that is our data, input data. So that goes into the learning algorithm. So in our case, we are talking about the linear regression algorithm. So learning algorithm is going to learn from the data, and what is it going to produce? In this case, for a linear regression equation, algorithm, it is going to create a a model which is essentially a linear equation just in this form. Okay, so y equals to theta 0 plus theta 1 plus x1 plus theta 1 x1 plus theta 2 x2 plus going forward to theta n xn, just like this. Y equals to, I mean, this is another notation you may have learnt in schools and colleges, that if you want to represent a function between y and x, so you can represent that by y equals to f of x. So that essentially means that function of x, y equals to function of x, and this function here is a linear equation. What is the linear regression algorithm learning in this case? All right, so you know y. What is our y in our in the case simple example that we were looking at? It is the sales dollar, sales figures. What is x? X is our advertising spend. Okay, is there an x2? No, I mean, we have a simple example, a toy example. We don't have any x2 and we don't have any xn, so we only have this equation up till y equals to theta 0 plus theta 1 x1. Okay, but in case you have more than one, so we have one predictor feature, but in case you have more than one predictor feature, your form, your linear equation takes this form, right? So what does the machine learning algorithm learn? Okay, so you know y and you also have x, but you do not know the value of theta 0 and theta 1, and these are called the model parameters. Okay, and these two values are the ones that the machine learning algorithm learns. So it goes through all the input data that is fed to it, it uses all the y values and the x values, and it feeds it into a learning algorithm. Okay, in our case it uses an approach called gradient descent. I mean, we can't get into gradient descent, that takes some explanation, so it's not possible to explain gradient descent very well here, but it uses that approach, gradient descent, to learn the optimum values of theta 1 and theta 2, so that our equation here is going to be the best fit equation between advertising spend and sales. And in case of multiple linear regression, you can also have multiple explanatory or predictor variables. Okay, so this is what your model learns, this is what your model creates. So model learns in machine learning, this is pretty generic, I mean generic concept to machine learning. The in machine learning, after the learning process, the model learns the model parameters. So in this case of linear regression, it learns the model parameters theta 0, theta 1, theta 2 to theta n, depending on how many explanatory variable or predictor variable that you have, right? So it is actually going to, your model is actually going to look like something like this. So if you have let's say x1 2 3 5 explanatory variable or predictor variable, then this is a fictitious example, but your model is actually going to look like this, right? So your linear regression model is going to look like this. All right, 3x1, y equals to 3x1, 4x2, 2x3, etc., etc. And this is a constant or bias term, which is we will look at the explanation of this. This is also called intercept for linear regression, and we will see what that is. All right, so this is clear. What does it what does your machine learning algorithm learn? All right, so now machine learning algorithm, we'll go over this very quickly. Machine learning algorithm learns the model parameters. Now how does it learn? It uses a approach called gradient descent, which is basically an approach which initializes the model parameters theta 0, theta 1, theta 3, theta 2, theta 3, etc., etc., with some random values to start with, and it goes on stepwise, and at each step it tweaks the value of theta 0, theta 1, theta 2, etc., etc., in a way that it minimizes or maximizes a cost function. What does that mean? That there is a calculation or there is an equation which will be minimized, which is a indicator of how good or how bad the model looks like. So in case of linear regression, the most used cost parameter are MSE or mean squared error, which is essentially the equation of all actual values minus corresponding predicted values squared and summed divided by n. N is the number of observations that we have, or number of observation is the number of rows in your data set. Okay, in simple terms. All right, so gradient descent plays with the values of theta 0, theta 1, theta 2 to theta n, and that is the model parameter, starting from a random set of values, and in each step it tries to tweak it in a way that the value of MSE or mean squared error is minimized. Okay, it goes into the it keeps on tweaking the values of theta 1, the model parameters, in a way that the MSE keeps on going down. All right. And the other cost function that linear regression uses is the coefficient of determination. It is also called the R square. Now R square is the equation that is equal to 1 minus RSS divided by TSS, and RSS and TSS is RSS is SSR, which is sum of squared residuals. So essentially the equation is similar to MSE. It's just that it is not divided by the number of observations. So you have this divided by n, and it does not have the divided by n. So it is a summation of squared residuals. What is the residual in machine learning parlance? In this case, the residuals are the differences between individual observations, actual values, and the predicted values. So how many times this is going to be, how many expressions you are going to have for your data for y minus y hat is equal to the number of rows that you have here. Okay, for each case there is an actual value that you have during the training process, and by your gradient descent step will use a value, use a model parameter value, I mean set of model parameter value, and feed the explanatory variables and find out the MSE of that particular step by or SSR in that particular step by summing up the residuals for all observations and squared, right? So again, going back to coefficient of determination, it is 1 by RSS by TSS. TSS is the total sum of squares, is the sum of squared squares of the differences between the predicted value and the mean of actual values. Okay, so that's what briefly our cost function and what or how the machine learning algorithm or linear regression algorithm in this case is going to find out the model parameters, the optimum set of model parameters, which are theta 0 to theta n. Okay, so a little bit of explanation of cost function. You need to understand a couple of things here. One is, say these blue ones are your actual data. Okay, so actual data are coming from your values here, advertising spends and sales. So advertising spend is your is along the x-axis, so this is your explanatory variable or x variable, and this is your y variable. All right, so if you plot these data points on a two-dimensional surface along x-axis and y-axis, this blue dots are, let's say, your actual data points. Then you run your machine learning algorithm, and you are going to predict the y values against each of the observations. So let's say, for instance, for this observation, okay, so this value of x, what is the value of y given our equation that our model has found out. Okay, so this line represents, it is a best fit line, and it represents the equation that our model has found out through its learning process. Okay, so then after the model has found out the best fit line, what you do, you predict. Okay, predict using what? Predict using the x values that you have got. And what do you predict? You predict the value of the target, that is the y value. All right, so if you do that, then your predicted values are going to be on the best fit line. Of course, it is going to be on the best fit line because you have used that best fit equation or linear equation that your model has given you. Okay, so it is going to be on the best fit line. Now here is your actual data, and here is your best fit line, right? Now what is your target variable? Your target variable is y. Okay, so along the y-axis, the residual for each observation is the difference between the actual value, actual y value, and the predicted y value. Okay, so this line over here is a residual. So this is a let's say negative difference, and this is a positive difference. So for each of the actual and predicted, you have a amount of residual. So what translates into a good model or a good best fit line is one, or is the equation whose best fit line, or the equation where the total amount of residuals, so that is reflected by your MSE or SSR or RMSE. Okay, each of this cost function reflect the amount of or total amount of residuals in different shapes and forms, or even your coefficient of determination, which is r square, is a total. They all reflect the total amount of residuals is counted or calculated by this plus this plus this plus this plus this. Okay, now there is a catch here. Here is a negative residual, here is a positive residual. So if you calculate all of this, and if you do not nullify the sign of these amounts, then they are going to kind of come to something near to zero or even zero. So and that's not what you want to find out. You need the total quantum, and that is exactly why in your cost function it is the residuals, that is the difference between y and y hat, which is the actual and the predicted values of your y variable, which is the target variable, are squared. Okay, the squaring nullifies the effect of the signs plus or minus. Okay, so you don't get to a zero value of your residuals, in this case you get to a value which is this quantum and this quantum and this quantum and this quantum. Or the other way of doing it is to use your absolute value, right? Some explanation about physical significance of r square. The r square is a value that hovers that is between 0 to 1, where 0 reflects absolutely no correlation between the data points in your data set, and 1 reflects absolutely perfect correlation between your data points. So essentially what we are saying is that when your best fit line has a r square value of 1, then your actual and predicted will look like this. Okay, so your predicted values will coincide perfectly with your actual values, right? If it is, let's say, 0.7 or 0.8, you see that there is still some correlation. If you look at the formation of the data that you have, you still have a linear relationship between this data. Okay, and in this case there is more or less no linear relationship between this data that you have, and this then the for this particular case there is absolutely no linear relationship between this data. Now gives us a question, is that if our data is this or this, should we even try to use linear regression algorithm for finding out a correlation between these data points? No. That is one of the key assumption of your of our linear regression model, that if your input data set does not have linear relationship, like your data is looking like this, then it is a futile effort to try to find out a best fit line for that particular data, right? Then linear regression is definitely not going to solve your problem that you are trying to solve here, right? So that is one assumption that linear regression has, that if your data set does not have a linear relationship between its features, between its target and predictor features, then there is the linear regression equation is not your right solution. There could be other equation that may be suitable. Let's say, for instance, if there are still patterns but not linear pattern, there could be polynomial equations that are suitable for solving your problem, if there is a polynomial relationship between your data. So those are discussions of another session, but here is a little background of what is linear regression. Now the problem statement that we are going to work with in our coding example is that there is a car sales agency. They sell second-hand cars. So people like you and me, I mean, we have used a car for 5 years, 6 years, 7 years, and we want to sell it and buy a new car. So we go to a old car sale agency, and we go to them and we tell them that, okay, this is my car, and can you please give me a valuation and then buy it. Okay, so they buy and then they sell to other customers, because there are a lot of people who want to buy old cars at a cheaper price, right? So that's what our company does, and what this company wants to do is that okay, so they employ physical inspectors. So there are people who actually come to you and say, okay, this is your car, and let me inspect blah blah blah, and they give a valuation. So that it's based on their experience, right? Now these guys have sold tens of thousands of cars over the last many years, right? So they have all this information that, okay, if they have sold let's say 50,000 cars in the last 10 years, then for all those 50,000 cars they have all the information about the cars, like, say, for instance, what is the mileage, what is the length of the car, width of the car, make of the car, year of make of the car, total cylinder size, horsepower value, etc., etc. Okay, ground clearance, all of those important features that a car has are there in their database. Okay, and along with that they also have a field called the price, sale price, at what price they have sold it. Now if they have all this data, it seems that is a good candidate for using a linear regression problem, that okay, we will create a model for them which is going to remove or eliminate the need of this physical inspector. So they are going to the customer is going to come to them and they are going to ask all these questions from the customer, and then feed that in, and then the model is going to give them an estimated sale price. Okay, so the physical inspection and valuation process is going to go away, replaced by a linear regression model, and we are assuming that there is a linear relationship existing between the predictor variable or the influencer variable, which are like your car's make or year of manufacturing, cylinder size, horsepower, mileage, and etc. etc. Okay, so that is our problem statement. All right. Okay. So with that, let's look at the worked out example of our problem to predict sale prices of second-hand cars using our linear regression model. All right. So the problem statement is clear. We go on and import a few libraries: the NumPy library, Pandas library, etc., matplotlib and Seaborn for visualizations. And let's import our data set, which is in the form of this CSV file called price assignment, car price assignment.csv. So read CSV is going to import our data set, CSV data set, into this data frame called cars, and this is our how our data looks like. Okay, so there is a lot of data. We have 205 rows and 26 columns. Okay. All right, so the problem that we can immediately see is that there is a lot of textual data or categorical data that you can see. So we have Alfa Romeo, there is a Audi, Volvo, etc., which are the car names, fuel type, gas and diesel, etc., aspiration, standard or turbo, etc., door number 2, 4. There is a lot of textual variable which are categorical variable that are not numeric, so these have to be converted into numeric digits before we get into the linear regression modeling. Okay, so all of that we will see. Okay, so let's check whether we have any null value issue. So we are using the cars.info, so dataframe.info function. What it is returning is that 205 not null values for each of this column. So that this means all of this 205 mean that we do not have any null value problem. None of these features have any null values within them, so we don't have to deal with that. We are not going to do a lot of exploratory data analysis. We are going to look at focus on linear regression modeling only, because the entire project in its original shape is going to take a few hours to completely go through. So I have reduced it down to a smaller size, only the essential steps to explain it to you quickly. So what we are going to do to start with is splitting the company name from the car name column. So we are not going to use the car name. So let's say this particular one is a Alfa Romeo. I mean this is also a wrong name actually. It's not Alfa Romero, it's Alfa Romeo Gilia or Gilia, whatever that is, or Stelvio or Quadriflogio or whatever that is. So we are going to drop this car names and we are only going to retain the brand names. So that is what we are doing here. So we are splitting that and we are only transferring the company name into this company name field, and we are creating a new field and replacing that value, replacing the make name into this field. Okay, the company name. All right, so we have actually parsed this old values and dropped the car name and retained only the company name, which is the brand name. Okay, and we have also dropped the car name field. All right, so so basically this was the old feature, and this is the new feature with only the make. Now there is a bit of a problem that in your data, see, this is a problem that in real life you will always face if you are a data scientist or a machine learning engineer, that you will not have clean data. Okay, so for instance, Alfa Romeo is spelled as Alfa Romero for some reason. In some cases, Mazda is spelled as Mazda. Nissan is sometimes having small letters and sometimes capital letters. Porsche can be have a different name. Toyota is having a spelling mistake. Volkswagen having a spelling mistake, etc., etc. So all these things you have to kind of visually inspect, use some techniques to inspect if there are anomalies in the data, and you have to take care of them. So what we are doing is we are creating a user defined function called company name. I mean, this is only one statement which is replace. So essentially data frame name dot column name dot replace function, you pass the value to be replaced and with what value to be replaced, and in place true. So we are calling the replace name user defined function with each of these pairs, with the first one being the wrong value, and the second one being, so A1 being the wrong value, and the B parameter being the correct value. Okay, so we have now taken care of all the wrong names of car brands, right? Then what we are going to do is that, and this is on your discretion, you may feel that instead of these two fields here, CT MPG, basically MPG is miles per gallon, miles per gallon in CT and miles per gallon in highway. So there are two fields existing. Instead of that, we want a field called fuel economy, and this expression is actually calculating a percentage from the fuel economy of these two fields, and storing it into this new field called fuel economy. Alright, so this is called feature engineering. Sometimes you may feel that a particular feature which is not there but can be derived from the from existing fields are more useful than the existing fields. Okay, so in those cases you can derive new fields. Okay, that's feature engineering. Now there is one downside of feature engineering, is that if you are deriving a new value from an existing value, then what is going to happen is that now you have created a new field which has a direct relationship called multicollinearity between this and this and this and this. Okay, which is undesirable for your modeling process. All right, multicollinearity is not desirable for your machine learning modeling. All right, so at some point down the line you have to make sure that you do not have multiple fields that have relationship between them. What we also want to do is that we want to create a new field called cars range and fill it with values which is high, medium, or what are that, budget, medium and high end, based on the values of the car, prices of the cars. Okay, so this is the price. So based on the range of the prices, we want a categorical value in this new field which will be budget, medium and high end. So when will we have a budget category there? If the range is 0 to 10,000, if it is between 10,000 to 20,000, it's going to be medium, and between 20,000 to 40,000 is going to be high end, right? So that's what we want to do. Again, this is feature engineering. So you are creating a new field based on bins, or bins are a term that we use for categorization or range based categorical values for our features, right? So our bins, there are three bins that we have created: budget, medium and high end, and we have used these bins in this new column. And then I'm not going to explain the entire code, but notice this function called cut. Now function cut applied on a data frame, and it's given by, I mean, this cut feature is coming from pandas data set, is going to return the correct bean values when supplied with the input value. What is your input value in this case? The price values from all the observations. All right, so it takes the price values from all the observations, and it takes the list called beans, and in this list called beans you have defined the ranges, right? Okay, so that's the second parameter. And in the last parameter you have the labels. Okay, the bin labels. The bin labels are this. Okay, so this is another list where you have stored the bin labels. So this cut function of pandas is actually returning returning a value for this cars range new field in your data frame when supplied with the price values, corresponding price values, and the bin definition and the bin label definitions. Okay, all right, so we have created, so this is another example of feature engineering, and then we see another example of analysis of our data. Now we said that between our fields we should not have multicollinearity or relationship existing between features. I mean, relationships, what are relationships? Relationships are like okay, I have one field x1 and another field called x2. If there is a phenomena that if I increase the value of x by 1, the value of x1 by 1, the value of x2 goes up by 1.3 or let's say 2.7. Okay, so there is a relationship existing like this, and that is undesirable, right? So your modeling process, during your modeling process, the learning algorithm needs fields or features that have an influence on the overall model or the relationship between the predictor variables and the target variable, but it does not want multiple variables to have the same influence. Okay, so in this case x1 and x2 are having the same influence. I mean, the rate at which the relationship between x1 and y are going to be exactly same, maybe different in scale, but exactly same relationship between x1 and y and x2 and y. So this is multicollinearity, and this is not desirable, and that is exactly why I have said before, when you have done a feature engineering and created a new field called fuel economy, you have created that from these two fields, CT-MPG and highway MPG, and you have kind of created a multicollinearity or relationship between these fields. And how is the multicollinearity? Let's try to define this multicollinearity again. How is this relationship now defined when you have created this fuel economy from these two fields? The relationship between these three fields are that each of this combination of each field of this combination of three fields will have a direct relationship with the other two. Okay, so fuel economy is dependent on this two, CT-MPG is dependent on this two, or highway MPG is dependent on this one and this one. So if you know the other two, you can easily calculate the remaining one. Okay, which is a relationship existing and which is not desirable for your model. So when you want to have derived variables, just make sure that you drop one of them if you have these combinations of 3 or 4, or if it is 1, then you are creating a direct relationship, one-to-one multicollinearity relationship between your variables. Okay, so you need to drop one. All right, so how do I find out the level of or degree of relationship between different features? There is this function called core, and when applied on a data frame, what it does is that it creates a matrix in the form of a data frame, and in that matrix, all the columns and all the rows are actually all the fields or all the numeric fields from your data set, which is cars, our data frame. Okay, and each cell is so let's say car width and wheelbase. So this is the intersection of the fields car width and wheelbase. So this the value in the intersection in this correlation matrix has a value which is called the degree of correlation or correlation coefficient. All right, now The correlation coefficient is a value that kind of ranges between -1 and +1. -1 means a perfect negative correlation. So that means if x1 moves by 1, x2 moves by -1.2, say for instance. So that's a perfect negative correlation. In case of +1, there is a perfect positive correlation, and 0 means there is absolutely no correlation between these two fields. So we have a value here which is 0.79. So that means 0.8. It's a very high degree of correlation. Now I will be worried about this pair of car width and wheelbase because they have a very high correlation and my model does not desire that, right? So what I need to do is that I need to find out, and this is very complex. I mean, going through this many number of rows and columns and cells is visually very difficult. So I need to find out an easier or more visual way of dealing with that. So what I do is that, and again you can stop the video in the recording. We will upload this into my YouTube, and you can go through this code. What I have done is that created a code where the absolute value of the relationship which is coming from your core data frame, which stores your correlation coefficients, and within a loop of repeating or iterating using the counters I and j, and we are using ILOC and index values of I and j to extract each cell value from your correlation matrix and finding out if the value is or the absolute value. Okay, so it can be minus 0.8 as well. So we are using the absolute value. If the absolute value is greater than 0.8, we are taking the two column names and adding it into a set called correlated features. Okay, and also printing this for our diagnostic. So this particular pair, car length and wheelbase, they have a correlation coefficient of 8.7, which is very high. Okay, so for instance, this particular guy, this highway MPG and city MPG. Okay, I mean, this is kind of no-brainer that if a car's highway miles per gallon is high, then city miles per gallon is also going to be very high. So they have to be very highly correlated. So it's so, but then we can't have both of them in our linear regression model. Okay, so so you will do some visual inspection from this data that is presented to you in the form of this diagnostic, and you will also use some business analytics mindset and some degree of domain knowledge to find out which of these variables are you going to drop. Okay, so correlated features, this set which I am displaying here, is all the fields which are like are in a pair are having high degrees of correlation. Right now we are not going to drop all of them because, say for instance, car length and wheelbase, we can't drop. If we drop both of them, I mean they are very highly correlated, but if we drop both of them we lose information. So we have to decide which one to drop. Okay, so with your domain sense and domain knowledge and some business analytics mindset, you decide as to which of this from this set of columns are you going to drop. Okay, which are more important to you, and which are which you are going to kind of retain. Another visual way of as we said that okay, it's very difficult to visually inspect this complex matrix. We also have another feature called heat maps. So heat maps, so we have taken the we have created another matrix called core-H, which is again in the form of our data frame with only those highly correlated features, which is this one, right? And we have this updated matrix. So these ones are all highly correlated, and we have displayed a heat map, and it's a SNS heat map, C-bound heat map, which you have passed the correlation matrix, the updated correlation matrix with highly correlated features. All right, so if you see that according to the color bar, there are a number of dark cells, and the dark cells have very very high numbers of or high values of correlation coefficient. So let's say this one here is 0.97, 0.99, etc., etc., and that is because these are the variables which are highly correlated. So you expect to see those very light numbers or very dark or very light cells or very dark cells in this heat map. All right, then what we are going to do is, now what we have not done here is, in the previous section, is that we haven't decided to drop any field, and we just decided to go ahead. Now in real life situation, when situations, I mean your problem statement is very complex, your data is very complex, at this stage you will probably decide to drop some fields based on the correlation values, but we have just, I mean, just for example's sake, we have retained those values, and we are going to test other methods going forward to find out our optimal model. Okay, so we haven't dropped any feature based on high correlation coefficients. Okay, now the next set of feature engineering that we are going to do is, we have a lot of categorical features. So initially we have said that there are a number of textual variables, and all of them are categorical features, so they have value options. So let's say, for instance, fuel type has two possible values, gas and diesel. Aspiration has standard or turbo, or say for instance fuel system has MPFI or SPFI and SPDI, etc., etc. So that's a kind of cylinder pattern. Okay, then what you need to do with this, and we said that all these features have to be converted into numeric fields. Now for textual categorical fields, if you want to convert them into numerical fields, the process to do it is one-hot encoding, or in other terms, we have to create dummy variables. All right, so what are dummy variables? So for instance, for fuel type, where the possible values are, or say for instance car body, the possible values are convertible, hatchback, sedan, wagon and hardtop. So when we create dummy variable for the car body feature to convert that into numeric fields, okay, so it is going to create 5 different dummy variables. Okay, one each for each possible values in that particular original field, which is car body. Okay, and what is it going to do with those additional fields? 5 different fields against the one original field is, for convertible feature, the additional convertible feature, that the dummy feature convertible, it is going to store 1 where in the original field the value was convertible, and for all the other rows it is going to fill it up with zeros. For the hatchback field, it is going to fill those rows with 1 where in the original field the value was the value was hatchback, and all the other rows in the hatchback, new additional hatchback field, it is going to fill with zeros. This process is called one-hot encoding. Now there are 2 things that you need to do. One is you have to drop the original field, so all these textual variables after creation of the dummy variables have to be dropped, and the second is one of these 5 additional fields that are created have to be dropped, because each of them are explained by or have linear relationship with the combination of the other 4. Okay, so that is multicollinearity, and from this additional fields of each combination you have to drop 1, and normally we drop the first one using a parameter called drop first along with the get dummies function, the pandas get dummies function, which creates this new features automatically. All right, so that is what we are doing here. So you can stop the video and in YouTube and look at the code. I'm not stopping for explaining the code. And then if you use the info function on your new data frame, you can see all these dummy variables are created. So say for instance the engine type, sorry, DOHC, SOHC, etc., OHCV, etc. So for these fields are created against engine types. So similarly, so many different so many additional dummy variables are created. So now if you look at the shape of this, so same number of rows, but instead of 26 original rows, original columns, you now have 69 original column. It has made it very complex, but we can't do anything about it. We have to convert our textual categorical variables, and the only way we can do it is creation of the dummy variables. All right. Now in a complex situation, when you are when you have more sophisticated means in your hand, after creation of so many different variables in form of dummy variables, if you want, you can go for dimensionality reduction techniques like TSNE or principal component analysis, etc. So that's not part of this session. We will probably have another webinar workshop on that, one of the dimensionality reduction technique, but that is something that you can explore to reduce the number of features in your okay. So the other thing that we need to do before we kind of create our models, linear regression model, is scaling of the values. Now what is scaling of the values? So let's go back and look at our original data set. So this is our original data set. So let's say we have a field called symboling, and the values are 3, 1, 2, etc. And then there are other variables where the values are 88, 94, 99, etc. Another value which is 5000, etc. Horsepower in the hundreds, price in the tens of thousands, etc. Now if you see, these variables have different scales of values. So some are in single digits, some are in double digits, some are in 4 digits, some are in 5 digits. Okay. Now this different scales of values features pose a problem to the gradient descent algorithm, the gradient descent approach that linear regression uses to find out the minimized MAC value, the mean squared of error, mean squared of residual errors. That was our cost function, if you remember our slides. So what the gradient descent does is that it tweaks all the parameters, all the model parameters. Now model parameters are what? So you remember the model, that is y equals to theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x3, etc., etc. Now theta 1 is the coefficient of x1, theta 2 is the coefficient of x2, theta 3 is the coefficient of x3. Now if x1, x2, x3 are in different scales, some are in single digits, double digits, or some are in 5 digits, then the tweaking of the values of theta 1, theta 2, theta 3 becomes difficult for gradient descent, right? And because of which, whenever you use an algorithm which uses gradient descent to optimize itself, you have to scale the values by using two possible methods. One is min max scaler and the other is standard scaler. So in this case we are using the min max scaler. So what the scaling process is going to do is that it is going to bring it down to the same scale of 0 to 1. The min max scaler is going to bring the values of the fields down in a scale of 0 to 1. So if you look at, so there is a calculation that it uses. Now you may be having the question that, all right, if I compress the values of all these fields, I mean it sounds so weird, I will lose information, right? The answer is that you do not lose information. The information that your input dataset has in the form of means and standard deviation, and the calculation that min max scaler uses those calculation, and you do not lose any value, any variance information in both cases of standard scaler and min max scaler. So you do not lose information, you just compress the values in your features. All right. So once the min max scaler is applied, so basically, so you create a min max scaler object, and then you do a fit transform and apply that on your data. And if you see that we are applying that on certain fields and not all the fields, because your if you see these values, these are your dummy variables, and the dummy variables are already in the shape of 0 and 1, so they are already in the same scale. Car ID also, I mean, we are going to eventually drop this feature. It's not useful to us. Symboling, we could have done it, maybe a miss, but should have been included in the list of variables that were scaled. And all the other ones in varied scales are now scaled now, okay, using min-max scaler. All right, now then we are going to create or split our data into predictor, and which is response variable or y variable, and the set of x variables, which are the we are going to split the input data set into the y and x set of variables. So y is our target variable, which is going to be our price, right, and the remaining variables that we have in our data set are going to be the x variable. So we have y train, which is essentially the price, and then we are using the pop function. Pop function returns the popped feature, and then the data frame on which the pop function is applied is actually retains all the other features except for the feature that is being popped. All right, so df train goes into x train, so this is our x set and this is our y set, which is the target variable. All right, now we get into modeling. We create our linear regression model, and in our linear regression model we get it from scikit-learn linear model. We're going to use linear regression model, and what we do is we also import the stats model API module, stats model API module, stats model library API module, because we are going to create or initially experiment with our linear regression modeling using ordinary least squares algorithm, which is almost same as linear regression. There are some subtle differences. Okay, so we create a user-defined function in which we have applied the ordinary least squares function, in which we are passing our y and x set of values. All right, and we are going to call it from subsequent code. Now build model is our user-defined function. We pass the x set of values and y train of values, y set of values, and there are a few things that are going to be so, and this is being printed by this statement. We have created the model by using the ordinary least squares function from stats model, and the model.summary function is going to print out all the information about the model that you have created. Right now, what is our model? Our model, we said at the beginning, is the equation, the linear equation, which is the relationship between your predictor variables and the target variable, right? All the x1, x2, x3 variables and the y variable, right? Now what is your model learning? Your model is learning the coefficients. Which are the coefficients? Theta 0, theta 1, theta 3 from your linear regression equation, the generic linear regression equation. All right, so if your linear regression equation is y equals to theta 0 plus theta 1 x1 theta 2 x2, this model has learned after being trained on. And how are we training it? By using the fit function. Okay, so after the fit function is executed on that particular model using the x set of values and the y set of values, it has got a model which we can analyze. Right now we said, so which are the information from this statistics model statistics that are important here? R squared is important here, which is 97.5, which is very, very good. Now we said R squared value denotes the explainability of that model. So that means that in layman's terms is our model is almost 97.5% perfect and that is the predictive power of this model. Okay, now we normally use adjusted R square, which is a modified value of R square. There are some disadvantages of R squared value. We are not getting into those explanations, but we normally focus on the adjusted R square. So in our case, that value is also very, very high. So 96% is a very good number. Then the next set of values that we are going to focus on from the model statistics is the coefficients. Now this is what your model is, right? So we said it's going to learn theta 0, theta 1, theta 2. So this is theta 0, which is constant. Constant is not one of our fields. So this is the intercept, which is theta 0. Car ID we are eventually going to drop. We should have dropped by now, but anyway. Symboling is say theta 1, theta 2, theta 3 and theta 4. So these are your values that you are going to finally be interested in. These are the coefficient that the model has learned. Now the next value that we are going to be interested in is this p-value or probability value. Now what are these probability values? These probability values are of the null hypothesis, which says that car length field does not have any influence on the predictor variable y. In our case, the predictor variable is price. Now what is the probability in this case? The probability in this case is 10%, 11% almost. Okay, and there is a process by which we say that there is a baseline cutoff baseline value of 5% that this null value can be null hypothesis can be accepted on. Okay, so what that interprets to, if the value of this probability is greater than 5%, which translates to the value of 0.05, if it is greater than that, then the null hypothesis is probably true. That means that this field may not have any influence on the model. Okay, so the value of this value of for the car length field is 0.109, so almost 11% probability. So we are going to delete this field from our model. Okay, so we are going to optimize the model, and by dropping all the fields for which this p-value is greater than 0.05. That's a kind of rule of thumb. Okay, so there are a lot of such fields where the p-value is greater than 0.05, and we are going to delete all of them. We are dropping all these fields which have a p-value of greater than 0.05, right? And then we build our model again by using ordinary least squares, right? And when we have our ordinary least squares created again, we get a modified model in which we have a lot less number of fields, and if you look at the p-value, they are almost gone. There are still existing. We will have to deal with them as well, but for most of the fields it is gone, and the model is still retaining a predictive power or adjusted R squared value of 94.7%, which is great. All right, so this is how you approach towards building a linear regression model. And the next thing that you should do is prediction. What I'm going to do is that there are a lot of other steps in this code. We are not going to go through that. We are not going to have time, but we are going to show you, jump a few steps, and we are going to show you as to how do you predict the data. So prediction using test data. So again, the same pre-processing you have to apply on the prediction on your test data, and you see that these values have to be scaled, and we do the scaling with the scalar fit transform. And after scaling, we go ahead. So let's say model 5 is the latest model or most optimized model that we have. After going through a few rounds of optimization using various techniques, model 5 is the final optimized model that we have created. And what we do is we predict using the predict function. Okay, using this model, use the predict function, pass on your x set. Now look at the difference. When you created the model, you had to pass both the x set and the y set, and in terms of in case of prediction, Of course, you don't want the model to know what is your predicted values. I mean, you already know, but in live situation you are not going to know. So a predict in a test situation or in a live situation is going to accept only the X set, so your X features or predictor features, and it is going to predict what the model is supposed to predict, that is the Y variable. All right, and then our R squared value, which comes from the scikit-learn's matrix module in the form of the R squared function. If you pass the X test and Y test, the Y test and Y pred value, so this is your Y values, your known values, your actual values, and these are your predicted values from the model. If you pass this to R squared, it is going to give you the R squared value for your testing, the model testing. And when you pass it the train set, the actual Y values from the train set and the predicted Y values from the train set, it is 92.53. okay, so when we build our model, the R squared value that we have got is 92.5, which is pretty good. For testing, the R squared value is 86.06%, which is not too bad either. All right, so this is how you approach towards linear regression. There is a lot more to it. There is a lot of exploratory data analysis that you need to do. There is a lot of adjustment or pre-processing or the data optimization that you need to do. If there are null values, you need to deal with that. There are various ways you can optimize your model, like say for instance variance inflation factor, VIF is one of the methods. RFE is another method that is commonly used for feature optimization in a model, which is recursive feature elimination model. So all of this, using all of that, you can keep on optimizing your model till you get to a perfect state. So this is our final model, which has this many number of fields, and it's adjusted R squared is 92.0 and R squared is 92.5, which you got from here as well. Okay, and what are the model parameters it has learned? These are listed here. So if you have how many fields that we have in the final model? 1 2 3 4 5 6 7 8 9. So x1 to x9 are there in our model, and these are the theta 1, theta 2, theta 3, theta 4, theta 5, etc. And what is this? This is our intercept, which is theta 0. Now what is theta 0? Theta 0 is the value of y when the value of all the x's are zeros. So if you just look back and refresh yourself with your knowledge of linear equation, the equation of y equals to theta 0 plus theta 1 x1 theta 2 x2 etc., that is going to make sense, right? So this is what we have in the linear regression introduction session today. So with that, we will close this session. Thank you for watching this video.